In this video, I want to have a look at some more examples of simple harmonic motion questions. So we're just going to jump straight into them. Our first example says we've got a particle moving in simple harmonic motion so that the acceleration is given by -4 outside of x minus 3, where x is our displacement. And we're also told that initially the particle is at rest at the origin. So that means that at t equals 0, the velocity is 0 because it's at rest, and the displacement is equal to 0. Part A asks us to show that the velocity squared is equal to 4x outside of 6 minus x. So for part A, we can start with the fact that we know that a half v squared is equal to the integral of the acceleration, which is our -4x minus 3 dx. So if we go through and perform that integration, I'm going to pull my -4 out the front, and then I can just integrate this bit here, which would give me x squared onto minus 3x. And then I've got to have a plus c, my constant, on the end there. If I go through and expand that out, that'd give me minus 2x squared plus 12x plus c. Now I can use these conditions that I was given to figure out what that constant is. So we know that when v is 0, x is 0. So that means, because I've got my half v squared here, if I sub my 0 in here, I'm going to have 0 equals, all these would be 0 because my x's are 0 as well. So that means that c is just 0. So we end up with a half v squared is equal to, I'm just going to rewrite these around the other way so that we're starting with a positive. So 12x minus 2x squared. If I get v squared on its own, I'd have 24x minus 4x squared. And then I can pull out, we're trying to get it to look like this. So I'm going to pull out a 4x as my common factor, and I'll end up with 6 minus x left in my brackets. So that is part A done. Part B asks us to find the equilibrium and the endpoints. So the equilibrium, so that's our point in the middle. If we have a think about what we know at that point, we know that acceleration at the equilibrium point has to be equal to 0. So our equilibrium point is going to be when this equation is equal to 0. So 0 equals -4, x minus 3, which means that x has to equal 3. So x equals 3, that is our equilibrium point. Okay. For the second part of that, it asks us for our endpoints. So our endpoints, what's happening at our endpoints is that our velocity would be equal to 0 because it's momentarily stationary before it starts coming back the other direction. So because our velocity is equal to 0 here, and I'll just write a equals 0 under that one so we know what we did, velocity is equal to 0, which means we're going to put this one equal to 0. So we'd have 0 equals 4x 6 minus x, which means that either x is equal to 0 or x is equal to 6. And that makes sense because they're evenly apart from that equilibrium, or I should say the equilibrium is halfway between those two endpoints. If it wasn't, we'd know that we had done something wrong. Our second example says that the equation of motion of a particle moving in a straight line has the acceleration, didn't mean to draw on that, has the acceleration equal to -16x. We're also told that if x is equal to 0 and v is equal to 0 when t is equal to 0, then we're asked to find the displacement at any time t. So we're asked to find x in terms of t, and then state the period and amplitude of the motion. So this first bit of information up here tells us that it is moving in simple harmonic motion, because for simple harmonic motion we know that the acceleration is -n squared x. So in our case, our n is equal to 4. Now when we first introduced equations for simple harmonic motion, we were using cos, but we can also use sine because they're just a shifted version of each other. In this one, to make things a little bit simpler, we're going to use sine. And the reason we're going to use sine is that because when x is equal to 0, t is equal to 0. So we know that sine starts at the origin. So what we can do then is we know that the displacement is equal to a sine nt plus alpha. Now because x equals 0 when t equals 0, that means we're going to have 0 equals a sine alpha, which means that the only way that works is if alpha is equal to 0. And that's just telling us that that sine curve hasn't been shifted anywhere. If we used cos, then there would be a value for alpha there because we would have to move it along so that it was initially at the origin. So that means our displacement becomes just a sine nt. But we also know that our n is equal to 4, so that means in this case we've got a sine 4t. Now that also means that the velocity would be equal to 4a cos 4t, and we can use this other piece of information up here to figure out what that a is. So if we substitute in v equals 4 and t equals 0, so we'd have 4 equals 4a cos of 0. Now cos of 0 is just 1, so that gives us 4 equals 4a, which means that a has to equal 1. So that means find its displacement at any time t. Our displacement equation here would just be x equals sine 4t, because that a was equal to 1. Now that value of a is also what tells us the amplitude. So our amplitude would just be equal to 1 because it's the value of the coefficient. And our period is, we can use this 4 to help us figure that out. So the period is always going to be 2 pi divided by n, and in this case our n is 4. So our period would be pi on 2. All right, so that's having a look at some different examples of simple harmonic motion problems.